Is the first section of chapter 2. We're looking at derivatives and rates of change. Now we talked about tangents a little bit from the last chapter. It's a line that only touches the curve once, and it goes in the direction of the curve. And then we also talked about how if it touches it twice, that's called a secant, right? So tangents where it touches the curve only in one direction. So the equation for our tangent line is a line that just goes through that graph just once and only touches it once. So if here's our curve, I have this point, so it touches it once, and the line for that is just gonna say I kind of touched it twice there, but so maybe it touches it once. So you might think, well, if I put a point right here, maybe that will be it, right? But no, it's going to cross. So it would just be that one. So as long as it doesn't cross twice, those be tangent, be like right here. And so that would be a tangent. So an equation for a tangent line, well, we need to know how to write an equation, right? An equation for a line. Well, that's three different forms, right? Y equals mx plus b. We kind of did a review on this. Y minus y1, point slope form, m times x minus x1. So I need a point there and a slope. And then we have standard form, which we can change everything into, where a and b, or my x's have to be positive, so my a has to be positive, and I can't have any fractions throughout the whole thing. Okay, so usually this one we always go here to start. Sometimes we just jump here and then solve for b and then plug b back in. But in order to write this line, don't I need some kind of slope and a point? So sometimes I'm given 2 points, so then I have to use, the slope equation in order to find that. And then I could use any one of these points to put in my x and y here, and then I could solve for b. And once I have b, then I could plug b back in. Or I can plug my slope in here and put my y in and x1 in for my point, whichever point you choose, right? So we did a review on this. So if we want to write the equation for a tangent line, we need the slope of this tangent line. So say this one here, we would need the slope of this line. So we'd have to calculate that, and then we could write the equation. And then we also talked about velocity and finding velocity, and we realized velocity is just distance over time. And so there we also needed to do calculate the distance between, say, the start distance and an end distance, or vice versa, and then the start time and the end time, or vice versa. Right, so really these two are actually the same, right? But in order to use these, we had to use 2 points, so we just got closer and closer and closer, right? We had this, we had this point right here, and then we picked another point closer, and we kept on using those to find either velocity or find our slope. So these two, velocity and slope, are the same thing, as at least average velocity is kind of the same thing as secant slope, because secant members too. Secant is same as a secant line, because the secant line has 2 points. So then we talk about instantaneous velocity. I'm going to spell this wrong, but I spell everything wrong. So, well, that's the speed right now, right? Instantaneous velocity is speed at that exact moment. Speed. I almost spelled speed wrong. Well, that's the same as our tangent, because the tangent is that slope at that point right there, at that single point. So it's the same as our tangent. And then we thought some more and went through and figured out that, well, the tangent slope and the instantaneous velocity is really the same as finding the limit as x goes to whatever that number is. So it's the limit of this slope equation, right? F of a minus fx over a minus x, right? It's that limit as we get closer and closer to that a value. Or switch those around. This should be switch those around. F of x minus f of a as x gets closer to a. So we realize that instantaneous velocity is really finding that slope, which is the same as taking the limit, is getting closer and closer to that point, right? So that's what we call the derivative. So the derivative is the instantaneous velocity, or that tangent slope. So that's what we're going to be doing in this chapter, is finding derivatives, that tangent slope or the instantaneous velocity. So here's an example for you. Find the equation of a tangent line. So that means we need a slope and a point, right? And so we're given this 0.11, so there's our point, and now we need a slope. Well, all we have is an equation, right? So I'm going to use the limit. So as I get close to this x value, 1, because all I have is 1 point. So to find that slope, we got our point, but we need a slope. I'm going to take f of x minus f of a, which is 1, all over x minus 1. So we'll calculate this. F of x is x squared, right? That's our equation that we're given. Plug in 1, I get 1. That's my y value. And x minus 1. Then I still can't just direct substitution like we did last chapter. We have to factor it like we did last chapter. So this factors to limit as x goes to 1 of x plus 1, x minus 1 over x minus 1. So those will cancel out, right? Because I'm multiplying, so I can cancel this out. So I just get the limit as x goes to 1 of x plus 1. Now I can go ahead and plug in 1, and I get 2. So that means my slope is equal to 2. So m is equal to 2. And now I have my point, 1, 1, and I have my slope. So now I can go ahead and write my equation, y minus y. And as long as it doesn't say what type of equation, I can put it in any form I want to. My slope, it's probably best practice eventually to get to standard form, probably. X minus x1, or x minus x1. There we go. There's my equation. I can transform it, add 1, y equals 2x, kind of thing. And I can put it in standard form, so 2x minus y equals 0. That would work too. So those are 3 different forms. So you could do this one. Here's another example. Here's my equation this time. So I'm just basically using the difference quotient. So my f of x minus f of a, my a is 3, because I need to find my slope. I'm given a point, so I need to find slope over x minus 3. So plug in 3 in the equation, I get 1. So this is minus 1 over x minus 3, and this is f of x, which is 3 over x. So I can't plug in 3 because I'm looking at the limit as x goes to 3. It would be 3 on the bottom, which is undefined. So I can simplify that to 3 minus x over x, right? I change this 1 into x over x. And then x minus 3, I'm dividing, so I flip it. So it's 1 over x minus 3. These are not quite the same. So if I go ahead and factor out a negative 1, I get a positive x and a negative 3. And this is multiplication. So now I can go ahead and cancel those. And so now I just get negative 1 over x, and I'm taking the limit as x goes to 3 for my slope. And so I plug in 3 now, and I get negative 1/3. So then I can write my equation, y minus my y value, which was 1. I should have known that. My slope, negative 1/3, x minus 3. There we go. So there's my equation for the line. You can put it in standard form. You can switch it. You can multiply both sides by 3 here. I get 3y minus 3 equals negative 1 x minus 3. And then that's easier to put it in at least standard form eventually. So you can simplify that now. And you could solve for y in mx plus b if you wanted to, or put it in standard form, ax plus by equals c. So that's why I did get rid of multiply both sides, so I don't have any fractions for that one. So like I kind of alluded to, or I actually said, right, this is really just the difference quotient. That's all I'm finding. I'm just have some type of x, right, that I'm going to a, and then it gives me a y value, right? That would be f of a. So I have that point. And then I just go a little bit further. I go a distance of, say, h, because I don't know what it is. So this point is a plus h. So that means that y value would be f of a plus h. And then slope is taking the difference of your y's. That'd be taking the difference of these, which is right here, and dividing that by the difference of your x's, which is just that distance h. So it's really just the difference quotient. So average velocity is really just taking the difference quotient, same as the slope for a tangent. So instantaneous, so like we did for the tangent line, to find the slope was the limit. So this is just the limit of the difference quotient. That's going to find our instantaneous velocity, because I'm just getting closer and closer to that a value. So I'm getting closer and closer. This is just getting closer and closer, where your h just gets, that distance gets closer and closer to 0. So that's why h is approaching 0 here. So really instantaneous velocity is really just taking the limit as h goes to 0 of the difference quotient. So here's kind of derivative notation. This says the derivative of f of x at a. So this means right here the derivative of f of x at a, meaning either 1, the velocity at a, or the slope of the tangent at a. So that's what f prime of a means. So f prime of a would be, since it's velocity, right? So it's the instantaneous velocity. So f prime of a is actually equal to the velocity at a, or the slope. Maybe I should slope at a. Don't even think it is the slope at a, but that notation is probably totally wrong. So here's an example here, finding the derivative of this function. So again, it's just more complicated, but it is the difference quotient. So I'm going to plug in a plus h, which sometimes we're used to doing. You could do an x plus h, that's fine too. So that means we're going to square that. Then we're going to subtract 8 times a plus h, and then plus 9. So that right there is equal to our f of a plus h. Then my f of just a would be plugging in a squared minus 8a plus 9. And then my h is just h. So when I take the difference quotient, f of a plus h minus f of a all over h, I'd be subtracting these. A little bit more room. So I'd be taking that top one, f of a plus h, which is a, probably should have gave myself more room. That's okay. And then this negative, I need to distribute it in there. So this is going to become, so negative f of a, which this is right here, would be negative, positive, negative. So negative a squared, positive 8a, and a negative 9. Now we can go ahead and simplify that, all divided by h. So square that out, distribute the negative 8. These 9s are going to cancel. Anything without an h is going to cancel, so this a squared is going to cancel. This 8a is going to cancel, and so you're just going to left with negative 8h and an h squared, positive h squared, and a 2ah, because when I FOIL this out, I'll get a 2ah, and then I can go ahead and factor that. H out of the top, so that's gone, that reduces, that's gone. So I get, say, negative 8 plus h plus 2a, and then the h is on the outside, and that will cancel with this one. So I just get negative 8 plus h plus 2a, and then I can go ahead and plug in my a and solve this equation. So whatever your a is, and okay, so they don't give it to you, so this would be your answer. That would be the derivative, so that's f prime of a. So here's another one. It's the same thing here. So this time on this one, it gives you an a right there at 3. So then I can use that at 3 to plug in for my a. So I had -8 plus h plus 2a. Oh, I guess I forgot to take the limit as h goes to 0. So I'm plugging in 0 there. So then I get for my slope or my velocity equation on the line, so that's looking for slope, that'd be just 2a minus 8. So then I can plug in my a. So then I get 6 minus 8, which is -2. So there's my slope, -2. And then I can write my equation for a line, y minus y1, my slope times x minus x1, and there's my equation for line. I can put it in whatever form I need to.